So welcome everyone for the departmental seminar. Today, as a departmental seminar speaker, we have Professor Joy Mitra. Professor Joy Mitra did his PhD at Indian Institute of Science, Bangalore with A.K. Rai Chaudhary. After that, he went for postdoc to Belfast. And since after that, he joined as an assistant professor at IISER Thiruvananthapuram in 2010, right? In 2010. So since then, he has been at IISER Thiruvananthapuram. And today he's going to talk about engineering homogeneities, skin homogeneities in MOS2 plates. So I guess this is very, very relevant for a lot of people here because I know a lot of people here work on TMDCs. So please welcome Professor Joy.
Thank you. Thank you, Shakib. Shakib had almost taken the wind away from the sails by leaving out the in part.
Yes.
And I was wondering, then what am I supposed to do now? He has taken away the in part. Okay. So hopefully it's not. Yeah. So it's inhomogeneities, and that's very important. Okay. So yeah, thank you for having me, Priya, Adil, Shakib. Very nice. A lot of familiar faces. So I'm from the School of Physics at IISER Thiruvananthapuram. Yeah, and that's our campus in the Western Ghats, and this is my group, which has actually, this is a bit dated picture though. In the last 1 year, both these two gentlemen have graduated. Now he's about to submit. These two have also left, so it's a bit of a depleted thing. And the work that I'm going to present today is essentially done by Hari, Arijit, Shravani, and Shashwat. Different and various aspects of whatever I'm going to blabber about today. Yeah, I'm going to blabber about today. And we are going to talk about transition metal dichalcogenides. I suppose many of you are quite familiar with the basics of these TMDC materials systems. Yeah, what they are typically realized is MOS2, WSE2, WS2, so on and so forth. What is very interesting out of all these very standard properties that I encountered, I'm a pretty recent entrant to the system, a couple of years old, really, was this zoo of quasi-particles, excitons, trions, bi-excitons, yeah, very quaint creatures. Unlike electrons and holes, which are charged particles and therefore guided by electric fields, guided and controlled by electric fields, where most of electronics works. That's how it works. Excitons, for example, are actually charged neutral particles. These are bound states of electrons and holes. So the most interesting aspect to me, why I entered or continued working in this area, was essentially trying to figure out how do I couple onto excitons, which are charged neutral entities, and how do I guide them, because they won't couple to an external electric field. Synthesis of TMDCs is also today broadly in 3 different areas. One is exfoliation. Even though it shows micromechanical or mechanical exfoliation, chemical exfoliation is also there. Physical vapor deposition and chemical vapor deposition. These are the 3 broad techniques using which TMDCs are experimentally realized. The samples that I am going to talk about today have all been prepared by a colleague of mine using chemical vapor deposition techniques. Now, given the 2D nature of these systems, they are actually susceptible to perturbations. They are susceptible to perturbations, and these perturbations may enter the system or influence the system in terms of its growth, in terms of defects, in terms of the substrate, and in terms of strain. What I'm going to talk today primarily is this 4th perturbation technique or strain in the system, where so that you have these monolayers or bilayers or trilayers of these ultra thin systems, literally a couple of angstroms thick. You have these systems, and if you strain them, their band structure, their electronic band structure, their phonon band structure, and therefore electron and phonon transfer, and the way they interact with the external world completely changes. And we'll see signatures of how strain actually influences or perturbs these systems. Now, my interest in TMDCs, a bit of history, was essentially due to a colleague of mine who actually makes these systems. And you can see here, this is WSC2, in some topography of that, and spiral-like structures. And this friend, this colleague of mine, he works on catalysis. It's an electrochemical study. And what he saw was that planar structures were less reactive than the spiral-grown structures. And the essential difference were evidencing these edges in a spiral-like structure. And this obviously nucleates due to dislocations, defects, nucleated in the growth process. And what we showed is that indeed the edges of these structures are highly conducting, much more conducting. So that's the DIDV map, or the conductance map taken through a conducting atom. And what we showed was that the edges are much more conducting than the planars, or the flat regions of the same substrate. And that was indeed very interesting, and that led to our initial publications in the area. We also worked on defects in the system. What you can see here is again WS2, tungsten disulfide. And you can see in this growth pattern, there are three very distinct regions and very symmetrically distributed, where alternatingly the system is conducting, non-conducting, conducting, non-conducting, again conducting and non-conducting. Phase segregated into conducting, or a higher conducting and a lower conducting domains, apparently on a homogeneous system of the same stoichiometry. Obviously, the reality is far from that it is a homogeneous system. Then you wouldn't see these things. So, so edge effects, native defects, all play a very crucial roles individually in deciding its optical, electrical, and optoelectronic properties of these very thin systems. So, what about strain? Over the past almost a decade, starting from 2010 onwards, a lot of very interesting work has been done on these TMDCs, indeed on graphene also, which is our 2D system, on how the properties of these systems change if you actually strain them. The most easiest way, or the straightforward way of straining this system is obviously to apply a uniaxial strain. You just put it on a flexible substrate, clamp it between two endpoints, and stretch them. You stretch them by piezoelectric means, by screw gauges, so on and so forth. That's uniaxial strain. You can also put it on bent substrates like this, and you go on plunging a plunger to the backside when the flat surface slowly curves up. And again, the MOS2 or whatever the monolayer you have stuck onto it, it actually gets curved. And if you have an idea of how beams bend and so on and so forth from your undergraduate education, you will fairly understand that indeed this system here, this green patch there, will actually get strained as you make the surface more and more curved. Both of these are essentially examples of uniaxial straining the system, primarily straining along this direction and along this direction here. Then, back in 2012, there was a very interesting study in which what people did was that they dug some pits. They dug some pits on silicon dioxide, put a monolayer of this TMDC on top of it, and then evacuated the environment. So obviously there was certain trapped gas molecules within the pit, and the pressure there, it was a tight seal, like a pressure cooker. As you evacuated the environment, what happened was that these monolayer actually bulged out. Now this is very different. Hopefully you'll be able to appreciate it. It's a bit different than just stretching a system or bending the system. Here, it is basically like blowing up a balloon. It's like blowing up a balloon with an internal pressure, trying to blow up or stretch the system. And this nucleates one kind of biaxial straining. It is bending the surface, but it is also biaxially straining the monolayer, because it is being strained in two perpendicular directions, x and y, at any point. So, and they saw, especially with the uniaxial and biaxial straining, people saw very interesting properties where these monolayer systems had fantastic mechanical stability. For example, here is a table taken from this publication here, which compares the mechanical properties of these systems in context to other highly stable mechanical systems. For example, graphene has a Young's modulus of around 1,000, carbon nanotubes of around 1,000. Stainless steel is of the order of 200, and you can see these lie somewhere in between. Yeah, around 2 to 300 gigapascal is their Young's modulus. They have fantastically large breaking strength. Okay, breaking strength which are much more comparable to carbon nanotubes than with traditionally very strong material systems like stainless steel. The other important factor which comes into these systems is something known as the stiffness. Yeah? It has a fairly large in-plane stiffness of 180 Newton per meter, and it has a breaking strength of 23 gigapascals. So comprehension of these numbers, at least to me, was very slow because I was not used to comprehending mechanical properties of these systems in isolation. So hopefully by the end of the talk, the relevance of these numbers will actually become clearer to you. But nevertheless, I just wanted to point out that the mechanical properties of this system are actually comparable to most of the strong material systems that we actually are accustomed to. What is additional is that all this is happening for a monolayer thin, yeah, a couple of angstrom thin system. Yeah. These are not big chunks of steel or blocks. Indeed, for graphene, if you look and compare the numbers, these are atomically thin systems, and that's what makes them so interesting. What makes them also interesting is that if you induce these uniaxial or biaxial strain in the system, their electron and phonon properties, their band structures, undergo a complete sea change and which are observable experimentally. And that is what this talk is about. That without breaking this system, without damaging this system by stretching, bending, twisting, we can actually stretch them or strain them, and then so you kind of you can stretch and strain this system reversibly, and then observe what kind of changes happen to the electron and phonon band structure and the ensuing transport properties.
Graphene's breaking strength is supposed to be higher. 13 GPa.
13 GPa breaking strength, yeah. Uniaxial breaking strength.
But it should be much higher than.
It's in percentage. It's in percentage.
Okay, it is much higher.
That is breaking.
Yeah,
no, breaking strength as a percent fraction of the Young's modulus.
Yeah, it's much higher. Sorry.
So, what do you think is responsible for it to, come out this way? That figure. That one.
The bulge.
The bulge. The balloon blowing.
What is responsible?
Yeah. What do
The
you think?
difference in pressure.
So you think some of the gas molecules are sitting here?
So the gas molecules are here. It was the system was immobilized on these pits. Okay, in nitrogen, if I remember the figure correctly. In a nitrogen atmosphere, it was immobilized there, and it forms a the leap of faith is this actually forms a seed kind of a pressure cooker edges. Yeah, okay, that's the only way it will actually form.
And graphene
drum and membranes. But the difference is that there we don't leverage the gas pressure inside so much. We look at the free oscillations. Yeah. But here we are actually leveraging that there is a tight seal here, and the pressure is not released when you are evacuating or putting the sample into a evacuated chamber. Yeah. The gas molecules have not leaked out. It's an airtight pit, and which is bulging up.
So, I mean, just one last question. So, do you have some idea about how much the strain was? Okay, we can.
It was around 1%. Okay, 1%.
So that's these structures then.
Yes. Okay. So you do realize. Yeah. Okay. So this is basically the idea of this work or this talk, that you reproducibly and reversibly try to strain these systems. Okay, and look at what kind of changes is brought about in the electronic amphonon band structure, in their transport properties, so on and so forth. Now, one inherent, what motivated me to do whatever we did was that yes, you can actually play all these very strange tricks on these systems, but the architecture of straining of what is described here, uniaxial, biaxial bending, yeah, these are not compatible with semiconductor or CMOS, standard CMOS processing industry. You can't have devices where you actually have a bent shape, or you're dynamically changing, or you have a screw gauge there, or piezoelectric crystals stretching. Okay, so while these architectures were very good for control, very reversibly, reproducibly, one could increase and decrease strain and look at its optoelectronic properties. As far as device fabrication is concerned, this was nightmare. Especially if you wanted to have a third or a fourth parameter coupled on, for example, temperature. Putting such systems, yeah, inside a cryostat and doing measurements is notoriously difficult. So what our motivation was to actually have strain inbuilt into the system in such a fashion, in such an architecture, such that I can actually fabricate devices where third, fourth, fifth parameters can actually be changed, like temperature, light, yeah, things one could change and then observe it as a function of those parameters. So let's see what we did. So what we did was we took a piece of silicon dioxide, and then on it we actually made these very small nanopillars of gold. These are nanopillars of gold, and you can see the typical diameter of these gold nanopillars are 300 nanometer with a periodicity of 1.5 micron. And we made these systems, and then we transferred these monolayers of MOS2 onto this substrate by a standard transfer technique. And you can see AFM topography of several samples here, where you have these periodic nanostructure of gold and the flakes, the triangular flakes or hexagonal flakes lying atop them. Okay, this shows a 3D rendition of this AFM topography, false colored, and what you can see is that, yeah, they kind of conformally drape these nanostructures. The height of these nanostructures are typically 50 nanometer in height, diameter around 300 nanometer. The periodicity we have varied, as you will see later, anywhere between 2 microns to 500 nanometers. So the periodicity of the nanostructures can change, but these two parameters remain constant throughout our investigation. Yeah. And what we see is, if you look here carefully, it's pretty clear here that around each nanostructure, you can see all these wrinkles being nucleated all around the periphery of the nanostructures. But not only are the wrinkles at the periphery of each of these nanostructures, they are all around them, but there are wrinkles extending throughout the flat region of the system also, with nanobubbles here all over the place. Yeah. So some of them might actually be debris, yeah, on the substrate, yeah, which kind of are residues of the processing, yeah, of the e-beam lithography, the removal of the resist, so on and so forth. Some may be surface debris actually drag into each of these positions. And you can see this completely rippled network structure which is actually formed. So this is a line scan of the cross section of a gold nanopillar before and after being draped with the MOS2 monolayer. So you can see the monolayer thickness is around 0.8 nanometer. You can also see this is the height of the pillars, which is 50 nanometer, which is the bare gold. You can see once the MOS2 drapes over each of the nanopillars, the effective width of the structure increases slightly, yeah, which would pretty much what would happen if you keep a water bottle on your table and put a large hanky on top of it. It will sag along the edges. Yeah. So what happens is it bends inwards at the top edge, then bends outwards at the bottom edge, and obviously sags and is unsupported for a good fraction. That is what we believe is the right representation of the story. Apart from actually these regions where it is heavily bent at 90 degrees or so, we also have these wrinkles. Now, wrinkles, we must understand that anywhere be it a bedsheet that you use, be it a tablecloth that you use in your everyday life. Wrinkles are formed as mechanisms of strain relaxation. Yeah. If you have a completely flat surface and let's say you give it a twist or you disturb it, immediately you will see to accommodate that strain that we have created, it will form wrinkles. Yeah. So there are obviously certain constraints, and as a reason of which the system gets strained, and then it forms these wrinkles as mechanisms of local strain relaxation. So let's see what happens optically, spectroscopically. This is a photoluminescence map, of that flame resting over the periodic nanostructures. And what we see is that exactly at the nanostructures, the intensity, the luminescence intensity is fantastically high, much higher than the regions between the nanostructures. Not only that, if you actually look at where the peak wavelength occurs, you'll realize that the peak emission at the strain regions, which is near the nanostructures, are all redshifted compared to the region in between the nanostructures. It is much more evident if you actually look at the individual spectra from each of these points 1, 2, 3, 4, 5, 6, and you will notice 5 and 6 are actually points in between nanostructures or the least strained regions. And if you actually look at the emission from the point 5 and 6, they exactly are the same as one would have got from a flat substrate, that is without any nanostructure. Yeah? Without any nanostructures also, there would be impurities, there would be adsorbates on the surface. So it's not obviously theoretically 100% flat. There will be deformations and nanobubble formation in those cases also. So that's what happens. But the moment you actually go to the nanostructures, the points 1 and 2, you look at it here, and you see that they are blue shifted, they are red shifted, they shift to longer wavelengths, and their emission intensity increases. There are other regions, for example, 3 and 4, which are much more intense. However, correspondingly, they are less redshifted. So, departing from the stable configuration, the equilibrium or unstrained configuration, we see a couple of sequences. In all cases, the luminescence intensity increases, the period intensity increases with varying degree of redshift. The ones which are most intense are less redshifted. The ones which are less intense are more redshifted. So in literature, if you look, as I said, a lot of work on uniaxial and biaxial straining had already been done. And the selling point of those studies were that they were extremely controlled studies. And as a function of straining, as a function of 0.1% strain, a beautiful calibration has evolved over the last 10 years or slightly more. And what people have seen is that today the wealth of previous reports allow us to actually have a fairly good calibration about strain versus redshift. So why will it redshift? So the understanding is that a monolayer MOS2 is a direct bandgap system. Okay? As you strain the system uniaxially, as you strain the system, the bandgap narrows. If the bandgap narrows naturally, the exciton emission will redshift because the bandgap has changed or decreased. Not only that, if you strain it beyond 0.5 to 0.6%, slowly the band structure changes such that the direct bandgap of the monolayer system evolves to an indirect bandgap. The indirect bandgap evolution, which takes place prominently above 1% strain, obviously decreases the quantum efficiency of recombination. And therefore, what we see here is that the maximally strained regions, yes, are redshifted. Yeah, they are massively redshifted, but their intensity is not that great because the system most likely, I think, in accordance with the previous experimental and theoretical understanding, have essentially turned out to be indirect bandgap systems now. This whole wealth of experimental and theoretical results then allow us to calibrate that depending on the amount of redshift of the emission spectra, we can back calculate what is the local strain on the system. And going on from uniaxial to biaxial strain, the redshift is typically of the order of 45 MeV to around 100 MeV per percentage strain, yeah, from this whole wealth of literature that is available to us. And if we assume them to be correct, what we land up with is that the strain varies in this as a function of these position of the monolayer over the nanostructures. It varies anywhere between 0.1% to 1.3%. So the take-home message from this is a redshift denotes the reduced band gap, and the intensity reduction essentially is tied with the change in the nature of the band structure, where the band gap changes from a direct band gap system for a monolayer to an indirect band gap system for the strain monolayer.
Like why the West is that's
right. Okay. Maybe I'll come to this a bit later. Yeah, that's a very pertinent question, and probably that is I said the scope of possible answers. Yeah, and the excitons. Yeah, it's more to do with that. I'll come to that. Okay, so let's see what actually the Raman spectroscopy. It's one of the most versatile probes in trying to look at the energetics, the atomic dynamics of crystalline systems, and what that gives us. Okay, so the two primary peaks of MOS2, which are the in-plane E2G and the out-of-plane A1G modes of the system. And what we see is, again, in line with what we saw for photoluminescence, the intensity of both these modes essentially increase exactly with the periodicity of the underlying nanostructures. So whenever this monolayer is on top of a nanostructure, yeah, the Raman scattering intensity increases much more compared to the regions which are away from the nanostructure or in between the nanostructures. Indeed, if you actually look at this data here, this the curve in royal blue, yeah, this blue curve in royal blue is essentially for an MOS2 flake on a flat substrate. Yeah, and if you look at it, the points in between 5 and 6, which are off nanostructure or in between nanostructures, their modes exactly fall in line with a MOS2 layer lying on top of a flat substrate. But the moment you go close to the nanostructures or on top of the nanostructures, yeah, you have to remember that Raman spectroscopy, photoluminescence spectroscopy, these are optical techniques. And optical techniques essentially do not have very large spatial resolution as much as the size of the nanostructures. The size of the nanostructures are of the order of 300 nanometers with a periodicity of 1.5 micron, whereas the best optical microscope, yeah, with the best of the numerical apertures that you can think of, yeah, which comes with even in a confocal setting, the typical spatial resolution you land up with will be around 700 nanometers to 1.5 microns. Yeah? So you can see we are not able to resolve individual nanostructures very clearly as much as in an AFM, which has much superior spatial resolution. Yeah. So for
field, right? Same with field.
Same with PL. That's what I said. Either with photoluminescence, any optical spectroscopy technique suffers from lower spatial resolution, and that was one reason why we kept the periodicity for these structures, yeah, the data I'm showing you, to 1.5 micron. Because if I brought it closer, if I brought the nanostructures closer, the same phenomena would happen, but these two bright spots would overlap each other, and you will not be able to resolve them experimentally. So there is a certain amount of kind of design in the experimental method that what are you trying to do? Yeah? Keeping in mind that these are optical techniques. So what we see is, sorry for digressing. What we see is both these modes actually kind of light up or become more intense on the nanostructures. Not only that, both the modes soften. Both the modes, the in-plane mode as well as the out-of-plane mode, soften as you come closer and closer to the nanostructures, and indeed with the regions which are maximally strained. Again, there is a wealth of information on the same groups who had done the photoluminescence experiment on the strain system. The wealth of information on Raman map, on Raman spectroscopy, Raman spectra of these strain TMDCs. And in that case, what we typically see is, if you take all that calibration into account, we typically see is that this is the red shift. Typically, the spectra shift by 5.2 centimeter inverse the Raman peak shifts for every percentage of strain. And if you apply the peak shifts which you observe here in these two maps, if you apply to these systems, you will see that these systems are typically 0.5 to 1.2% strain. Yeah. Okay. So first of all, it corroborates with the strain calculated from the photoluminescence map. So this kind of gives us confidence. So it also tells us that there is a softening of the lattice spring constant for the phonon modes in the system. Yeah, because these are after all coupling on to the phonon modes or the spring constant, oscillatory spring constant of the lattice. So this gives you a bit of the correlations of the system, and you can basically see here are the points 5 and 6, which are unstrained or the least strained, and you can see the PL intensities are the lowest. They are the least redshifted. Yeah, they are the least redshifted. If you look at the frequency of the Raman modes, they are the least disturbed. Yeah, and if you come to the more strained regions on top of the nanostructures, all across all these parameters, starting from the PL intensity to the peak position to the PL width to the peak shifts of the two Raman modes, they are all extremely correlated. And finally, as I said, from the calibrations, you can now put numbers on the typical strains in those regions. Here, the straining is the least or close to 0. On the points 3 and 4, the strain is of the order of 0.2, 0.3. And these are the maximally strained regions, which is of the order of 1 to 1.2%. Right. Having done this and being aware of the fact that optical spectroscopy data lacks spatial resolution, and since obviously I do scanning probe microscopy, we went back to looking at the AFM maps, and let's see what are the consequences of this training. So this is the topography map which I showed you earlier, yeah, with all these wrinkles, and let's see what we can actually get from here. So now we have, as I told you in the cross-sectional map, the system bends across the top edge of the nanostructure, and again bends outward at the bottom edge of the nanostructure. Okay, it is also bends and curves as it forms the wrinkles all around it. Okay, and now looking at the change in the height, the topographic height of the system, vis-a-vis the bare, undisturbed plane. Okay, looking at that height and looking at the curvature. Again, if you go back to your old textbooks, my college textbooks of general properties of matter, you will be pretty well be able to now make a connection between the local curvature on the system, yeah, beam bending, local curvature on the system, and the strain, the EZZ component of the induced strain on the system. Okay, so you can pick up any textbook starting from general properties of matter, anything to Landau difference, I suppose. Yeah, they all have the same formula. So in case you want a reference, yeah. Yeah. Okay. So in comes the Poisson ratio, yeah, which is 0.25. Yeah, in comes the thickness and the height, which is obviously measured. Thickness is an input. From our measurement, height is actually the topographic map, which we actually get, or the change in the height. And from here, then from the topographic map, we can calculate the local curvature of the system. Once we calculate the local curvature in the system, we can actually generate the strain maps. So the topographic height, the height difference, the curvature, and then it actually translates onto the strain maps. And it is showing you very clearly that, look, not only are these regions at the edge of the nanostructure strained, but all the wrinkles where they are heavily folded with fantastic radius of curvature. High curvature regions, yeah, very low radius. They are all strained. They are all strained. So now the question arises again, that why can't we see those structures in the optical spectroscopy maps? Unfortunately, just because of spatial resolution. Yeah? These structures here, the wrinkle structures, are typically 20 to 30 nanometer in width at max.
Quantum dots guys, like looking at specific small regions. I think they have spatial resolution.
Atom probes.
No, not atom probes. It's called single atom spectroscopy. So their resolution is of a quantum dot size.
Okay, so what are they measuring?
I mean, they can look at the optical,
No, I haven't done it.
because that could give you some.
Yeah, what? Yeah, okay. Okay. Maybe I'll talk to you about that. Yeah. Okay. So you have this strain, and now, so obviously, now that you have a strain map, you can see what is the range, and it is exactly in the range that we had back calculated from all this, calibration curves from this last 10 years data, as I told you, from the photoluminescence maps, from the Raman shifts, yeah, and it kind of, which is by which time we kind of gain confidence that maybe we are really speaking about correct things, because the strain from this very disparate range of experimental probes all seem to agree that the system is strained anywhere between 0 to 15%. Now, this kind of straining, sorry, 1.5%. This kind of straining, as you can see very clearly, is non-uniform straining. It's inhomogeneous. It is very different from the uniaxial or biaxial straining which people were doing earlier, okay, which was homogeneous. The entire system was uniformly strained, which is not the case here. Yeah, this is absolutely randomly strained. It's not really random, yeah, because it's all nucleated by the periodic nanostructures. But notionally, randomly, inhomogeneously strained the system, you just have a range of strain values. Okay, and this is what I was kind of trying to tell you, that if you look at now our calculations, the back calculations from PL and Raman, and the direct calculation from AFM, and you will see that these are typically the strain and the strain percentage strains which are nucleated across the system, very non-uniformly, extremely inhomogeneous. The add-on effect of all those strain experiments, the strain calculations, theoretical investigations, were that these strain systems, uniaxially or biaxially strained systems, okay, also change their electronic band structure. And what was the prediction? The prediction was that as you strain the system, the band gap narrows. The band gap narrows. And if you look at the typical strain numbers that we have got here, the estimated narrowing of the band gap of the system is of the order of anywhere between 20 to 130 MeV or 40 to 200 MeV, depending on this range of local strain at different points. At different points, you will have different narrowing of the band gap. It's extremely inhomogeneous. Okay. The other very important thing which I must point out, that you cannot see probably the red regions anywhere in the edges. Yeah, they mostly happen at the wrinkles, very narrow regions, not protracted regions, very narrow regions with the largest strain. So now let's look at more detail with the strain and the wrinkles. Okay, so this is again just it's a 3D rendition of the AFM topography, and it just helps you figure out and see the wrinkles, the way they have been nucleated, and how interconnected some of these wrinkles indeed are. And if I click it, and this is the calculated strain map, okay, from that fancy IISER model, and you can see exactly where the straining is actually happening. Now, when I saw this picture, the 3D picture, 3D rendition of this topographic map, this just reminded me, when I was at my young, we had this round table at home, and very often my mother had a tablecloth, which was fantastically big, and we used to kind of drape it on top of that. And if you actually look at it, yeah, this is exactly how the tablecloth would drape over that circular table, that circular tabletop. Yeah. At the edges, what would happen is, obviously under gravity, it would fall down, the tablecloth would fall down. But unlike a straight edge table, there was an azimuthal curvature of the table, right? So this simultaneous curvature along the z-axis due to gravity, as well as the azimuthal curvature necessitated by the structure of the table or the local radius of curvature, essentially nucleate the wrinkles on the table. Okay. So we cooked up a three-dimensional tablecloth model, literally, with the mechanical properties of MOS2, the right thinness, the right Young's modulus, the right bending modulus, and the right density, and allowed gravity to take over on top of these nanopillars. And if you do that, this is what you get theoretically as the lowest energy structure of this very ultra thin membrane of 0.7 nanometers. And this is exactly what you see, very similar to what we see here. We have kind of 4 cylinders here, because more than 4 it was becoming too cost intensive theoretically to actually do the dynamic calculation. And you can see these wrinkles which are nucleated exactly at the edges, and they extend between the nanostructures. Yeah, this is a more close-up of one of these things. You can see primary wrinkles which are denoted by these orange arrows here, primary wrinkles nucleated. You can also see secondary wrinkles nucleated slightly away from the edge of the nanostructure. Yeah, and what you do notice is that in between these regions, these green arrows, what it actually shows is that while the membrane bends in 2 directions, along the z direction, which is radial bend, and along the azimuthal direction, it periodically or alternately stresses and strains the system. So at regions it is compressive, in the next interval it is relaxed, where the wrinkle nucleates. Again, there is a compressive strain. Again, it relaxes, and this azimuthal alternating regions of strain and strain relaxed system is what sustains the wrinkles away from the nanostructures. Now, I was very skeptical because of a very simple thing. I was doing a theoretical model, okay, without apparently any asymmetry in the system. Yeah. So why would a wrinkle nucleate here? Yeah. Why would and believe me, if you repeat the calculations, as it turned out, I didn't do anything. As it turned out, due to the meshing or the finite element method calculation, yeah, statistically, you would get each time you redid a mesh, it would distribute in a slightly different fashion. So there is statistical variability in the structures which I am showing you. After I did the calculation, I came across one paper, a very interesting paper, and anybody interested in looking at the mechanical properties of ultra-thin systems, I would definitely encourage you to look at this paper, PNAS 2021. Yeah, 2021. Okay, so while simulating the wrinkles, what I did utilize is what is known as the classical wrinkler model, and these models were developed in the context of polymers. You stretch polymers, a thin sheet of cellophane or so on, how wrinkles would form for the packaging industry and various other things. Essentially, it turns out wrinkle formation essentially is a competition between 2 properties. One is the bending rigidity, which is connected to the Young's modulus of the system, of the membrane, and 2, the substrate sample interaction. Yeah, it's some kind of a force constant per unit area. So a competition between B and K essentially nucleates the wrinkles. How can we be sure that is indeed the case? Assuming that the theory is correct, it has certain predictability. It actually predicts that what would be the wavelength or the corrugation wavelength of the wrinkles nucleated. So you can do topographic experiments, which we have done, to show that indeed it actually follows the predicted relationship between the bending modulus of the system and the substrate sample interaction. This is an interaction, this is obviously a parameterized interaction, an interaction which is between the MOS2 monolayer and the substrate. And you can hopefully imagine that is a notoriously difficult thing to quantify, simply because it will change from substrate to substrate. If it is gold, MOS2 would interact very differently, presumably, than if it is single crystalline, let's say silicon dioxide, if it is a polycrystalline silicon dioxide. And indeed, I have been working for the last couple of months that give me some numbers, which allows me to estimate the value of this such a spring constant in the first place. Anyhow, what we did was that since we didn't have a number for the spring constant, however, we had a number for the bending modulus in terms of the thickness and the Young's modulus, so B was known to us. Yeah? And what we also knew was that the actual characteristics of the undulations of the wrinkles and what was the periodicity of the wrinkles, this is experimental. And so we actually went back and back calculated what would be the typical value of K rather than knowing K and trying to predict what would be lambda. Lambda is measurable. B is known to be. So can I actually predict K? And if you look at K, what is the typical spring constant? And if this number is actually a rational number, in many sense, energetically also. This is typically the spring constant via which the attractive force between, let's say, two graphene monolayers. Yeah? People have done theoretical calculations of two graphene monolayers being brought close and apart from each other. This number is absolutely in the same ballpark. This number is also in the same ballpark, for example, of extremely sensitive AFM probes. The same spring constant is what gives you the AFM topography, remember. So therefore, this is an extremely rational number. Certainly of the order of estimate, absolutely, but even of the order of 1, yes. Okay. Again, I would kind of encourage you to look at the same PNAS paper in 2021. Okay. A phase map, interestingly, in the AFM actually gives you much better resolution of the individual wrinkles, far better than the topographic maps or the strain maps or anything you do. So tapping mode phase map actually gives you a wealth of information, and it is from these data, and its Fourier transforms that we actually got this number lambda of around 30 nanometers. Okay, so strained, wrinkled, yes, all nice. How does it matter? How does it change the electronic properties? What is the reality? The reality obviously comes in terms of looking at the conductance maps and the current maps with a conducting AFM. And what you do notice is that these are kind of in tandem topography, current, strain, and conductance map. This is the DIDV, local DIDV, and you can exactly see the regions at which the strains are high. The strains are not uniformly high at the edges. Yeah? Remember, there are these regions of compression, azimuthal compression, and relaxation. So there are regions of high strain and low strain, high strain, low strain. Exactly in that fashion, we see that the conductance around the nanostructures change. Yeah, we can also see the secondary structures, nanobubbles, etc. The strain structures actually have large conductances and carry large currents. These are obviously for two different nanostructures and the strain features around it that you can see that the local conductivity and current maps change. Yeah. So again, our take-home message is that we have this localization of high strain at the edges, the wrinkles, and the bubbles, and which are accompanied by high local current and conductance. Just to kind of prove the point home, this again shows line scans over 1 nanostructures, and you can see the correlation between the current maps, the strain maps, and the topographic height around the nanostructures. And these are typically reproducible even at the secondary structures or the wrinkles around it. Okay. So we have regions in space which are highly strained. We have regions in space which are less strained, which means the regions in space which are highly strained with lower band gap, and the regions on the same sample, less strained, have larger band gaps. But that's exactly what happens when you actually go to junctions, heterogeneous junctions like a PN junction. Spatially, you have an interface, a region where materials of different band gaps meet. And that's exactly what we did. What we did was, based on the strain maps, we calculated the percentage strain. Based on the strain, we calculated the band gap narrowing. And with those numbers, we went on to solve the Poisson equation, as one would normally do for any PN junction or Schottky junction kind of system, where we assume theoretically there is an unstrained, strained, and unstrained region. So it's a unstrained, strained, and unstrained region with a commensurate band gaps. And we went on to calculate what would be the band bending at the interface across this unstrained, strained, unstrained region of space. And what we do notice is that we have obviously the red and the blue actually shows you the conduction and the valence band edges at equilibrium. EF shows the property of the effective Fermi level across in equilibrium across the 3 regions. and the green shows the carrier density. What we do see is that the carrier density is higher overall in the strained regions with a narrow band gap, but it is the highest at the edges or the interface of this strained unstrained region. So remember, those cylinders, the top of the cylinders were flat. They are unstrained regions. The edge of the cylinder are obviously extremely strained, and you again move away from the cylinder, it is unstrained. Or think of a ripple or a wrinkle. Exactly at the wrinkle is extremely strained. On either side of each wrinkle are unstrained regions which are flat. So that's the way periodically it will happen. Otherwise, you don't have a wrinkle. You have to have a flat region and a bent region and a flat region and a bent region. So the model is essentially based on the physical reality we were seeing under an AFM. And what we see is that the local band bending and electron density exactly pulls up and puddles up at the edges of those wrinkled regions. And that's exactly what we see in our conductance map and the current maps, which we saw in the previous slide. Okay, so essentially, from a schematic point of view, this is what more or less happens. Not exactly, because you can see there are a lot of other features which turn out in the process. But essentially, in the strained regions, these are the strained regions. In the strained regions, you essentially have a lower band gap. Yeah? You have a lower band gap, and in the unstrained regions, we have a higher band gap system. And I think to answer your question now, essentially, once you have this exciton formation, yeah, once you have an exciton formation in the flat regions, now excitons are charge neutral systems which won't be guided by an electric field, an applied electric field. You can't bias them and drive a current here. But look at the exciton binding energies over this energy landscape. Naturally, what is happening here, if this is correct, then is that the exciton energy here is larger and here is lower. So naturally, all the surrounding excitons essentially face a landscape not by electric field but by energy. They face a potential gradient, an energy gradient. And the understanding is that they would be funneled into these lower band gap regions. And naturally, when they will emit much more strongly because you have kind of drawn in excitons from your neighboring area, albeit with a lower band gap equivalent energy in the process. And that, to me, is the most exciting part today of EMDC research. And can that zoo of quasi-particles be harnessed for doing anything profitable? All this is fine, fancy structures, probing spectroscopic properties. But to take kind of really device physics, can we actually take these excitons and do something? Can we guide them? Can we control them? Can we tailor them? Okay? Can we channelize them to transport energy? Okay, and create and excite and de-excite at our instigation in a controllable fashion. Okay, so having done this, we naturally, the typical thing is, okay, so what happens to the electrical transport across these systems once we what time is it? Last slides. What happens to electrical transport along these MOS2 systems once you non-uniformly strain them? Okay, so this is the generic, PET architecture with MOS2, let's say, and then we put in these nanostructures where you kind of, non-uniformly strain them. And what was very interesting is that if you, okay, so these are now a series of optical micrographs, and you can see that this is an unstrained film, and here you have a series of films where the periodicity of the nanostructures have been changed. Yeah, it is 2 micron here, 1 micron here, 0.5 micron here, and what you can actually see is that that since the nanostructures periodicity is decreased, yeah, there are many more wrinkles from the AFM images. Yeah, a lot more bending per unit area. So therefore, starting from here to here to here, the film is much more strained per unit area, and the density of wrinkles and everything increases. So let's see what happens. To cut a long story short, these are all the characteristics, the IV characteristics, so on and so forth, the most important thing which we got out of this whole system was the mobility. Okay, starting from a CVD film which is unstrained on a flat surface, the best of the films we got. Yeah, you strain these films non-uniformly via these nanostructures. You essentially get almost a 60% or 60 times, sorry, a 60 times increase in field effect mobility as a function of gate voltage. Obviously, you can see, yeah, and then it drops. This is basically the gist of it. The mobility increases from something like 0.2 or so for a flat film, which I call zero strain. And as you go on increasing the density of nanostructures, we have no way of quantifying in this non-uniform strain in the system, but certainly per unit area, the number of wrinkles or some such parameter does give us a good enough number. So this is 4 times more strain, and it increases almost 60 times. 60 times. If you look at the fractional change in the conductance, it also increases for the maximally strained, 4x times strain film compared to the unstrained flat monolayers. This is a collection from literature just to contextualize where we stand. So if in the present work on CVD grown films, yeah, as you can see, we probably at the stage we did our work last year, it was the report of the highest change in strain in mobility of the system, and absolutely comparable to whatever was the maximum reported then, which was reported back in last year, 2022. Yeah. So now the question obviously arises that why does mobility increase with strain? Why would mobility increase with strain? Now, a typical definition of mobility within the scheme of group models would obviously be this. However, one should remember that sigma in these systems is probably not best described as any mu, which is the group model's signature equation, simply because any mu actually assumes that n is homogeneous, is uniform across the system. Whichever way you write your Boltzmann transfer equation, that is the basic assumption, and which is not the case. Yeah. There are various reasons why, or speculations as of now, why it can increase. Obviously, there are a couple of things. Is that the phonon scattering decreases. If you kind of use the KB theory to actually predict a change in the effective mass of the system, and you will see that even for medianly strained system in our case, we can actually see that it slightly decreases, which will, even in the simplistic picture, will aid mu. Okay. There is also very preliminary results which shows that if you actually bend these monolayers, it actually increases the dielectric constant. It quenches the phonon modes. Increasing the dielectric constant, increasing the local number density, so on and so forth, would obviously discourage Coulomb scattering. Would discourage Coulomb scattering simply because it would lead to effective screening, much better screening of charge transfer along the system, and therefore that would definitely benefit mu in some sense. Yeah, and that's a very interesting paper which actually did some experimental investigation into dielectric constant, again I think 22 last year on bent MOS2 layers, and it kind of showed that indeed the dielectric constant in plane and out of plane both are perturbed as you bend the systems. Okay. So finally, we have this is my last slide. So we have this non-uniformly strained monolayer of MOS2. We can't exactly control the strain in such a scheme, in such an architecture, by changing a screw gauge or a piezoelectric crystal voltage, but we can certainly control the overall strain in the system by controlling the periodicity of that underlying nanostructures. So that's one way of controlling the overall strain in the system, and we evidence very directly the change in the local band gap and electron density via the spectroscopic measurements and the local conductance measurements, and it does allow a degree of control over the electron mobility and transport in the system. Yeah. And as of now, I firmly believe that it's probably the ionized the screening effects of the ionized defects, which I have left out my temperature and transport effects, which also gives credibility to these speculations that it is indeed screening of ionized defects and Coulomb's factor, which has a very important role to play rather than phonons in the system. But I haven't gone into the temperature-dependent transport. Yeah. Well, yes. To put on this, my collaborators, my students, all these people who fund my research. Yeah.
So, thank you, Mr. Mitra, for such a nice talk. Questions? Students first.
You suited me instigated.
Yeah.
So in the strain part, you have shown the nanocrabs, right?
Yes.
Strain are most the periphery side,
Yes.
and the central part of the nanocrab is almost negligible,
Yes.
zero.
Yes.
You are so mapping.
Yes.
So the emission is coming from this periphery or central part?
Right. Right. Very pertinent question, and that's why I went to the spatial resolution of any optical spectroscopy. So you see, the size of the nanopillion is 300 nanometer. Okay. The optical spectroscopy techniques do not have the resolution to discriminate emission from, let's say, the center of the nanopillar and the edge of the nanopillar. Okay. So it just lacks experimental spatial resolution. There's nothing I can do about it. Yeah. There are alternate techniques of super high resolution spectroscopy and all, which we haven't done. Yeah. But the belief is, what I understand is that it is indeed coming from the edges, yeah, where the wrinkles are started forming. But when you evidence it experimentally, you are viewing it delocalized with a much lower spatial resolution, as if coming from the entire. So indeed, for the 0.5 micron or 500 nanometer periodicity structures, if you look at the PL data, you wouldn't be able to distinguish between these forms at all.
So I'm saying, you say that indirect to direct nature is very giving more strength. You have any density straight plot. Already monolayer must give you direct center, right?
That's right.
When you give you strength, you want much it is more lower, right? How much for you what you think?
How low, how the band gap? Yeah. So that's what I had. One of the slides. If I just go back, I had a. Yeah. So if you look at the this is a culmination of all data which has come out in almost the last 10 years, and you can typically see that the band gap lowering can range from around 10 MeV to 130 MeV for the most strained systems, and most strained I mean of the order of 1.5 to 2%. This is the amount of band gap lowering. The band gap of the system is of the order of 2 electron volts. I mean, the unstrained band gap of the system is around 2 electron volts. In a scale of 2 electron volts, anywhere between 100 to 200 MeV is typically the lowering. Yes.
You are using the nanopillar instead of nanopillar. If the hemispherical bubble
Yes.
is
Yes.
then there is a much more to control on the strain because the
Absolutely. Now, one thing is that fabricating experimentally a hemispherical dome, yeah, is probably notoriously difficult. Okay, creating a hemispherical crevice is probably far easier, or a pyramidal crevice is actually far easier than actually creating a hemispherical dome. So as much as I would have loved to have hemispherical domes all over the place, yeah, it's not very easy to do that. Yeah, and certainly in this or smaller lens scales.
hemispherical that must have the high control such that we can vary the strain because it is the diameter is very small of this nanometer.
Yes, but you should remember the EZZ strain, epsilon ZZ element which I showed, is actually depending on the local curvature. Yeah. So the scheme that you are suggesting will actually have lower local strain, much more uniform, yes. But if you actually look at it, it is the curvature, it's 1 by R. Yeah. So actually the wrinkles are the regions of highest strain because they have the highest curvature, the lowest radius. And it is the fantastic mechanical properties now, if you look back in context, and which allows it to bend in such low radius without cracking, breaking, without doing anything.
This is gold. So metal to semiconductor interaction, how we can distinguish the charge transfer and the
Yeah,
strain?
Okay, yeah, absolutely. Very brilliant question. I mean, since I work on plasmonics, I had all my alarm bells ringing all over the place. And what is happening? All this is rubbish. Strain is not the crucial factor. You are getting bogged down by the metal underlayer, this, that, and the other. I will show you. Okay, so if you do theoretically do calculate the plasmonic effect, you will see a particle of that size would have electric field enhancement, near field enhancement, beyond 1000 nanometer. And I am far away from that doing my experiments. Okay, so that was my first theoretical checkbox. Yeah, at least proof that I am not being interfered too much by near field effects. But now I can. But we didn't stop there. I'll show you some data on Al2O3 pillars. Okay, it does exactly the same thing. Okay. So I tried evaporating silicon dioxide. Even these small pillars break. So finally, it is easier to process metals. So you go into aluminium, oxidize aluminium, wet chemically or physically, yeah, and you do that. It does exactly the same thing, same structure, same size, and you can see you can pretty much make any sign image luminescence that you want. These are all on aluminium oxide, and you can see exactly the way wherever there is the ridge, yeah, you can see, and in between the ridges here, these are different architectures, but in between the ridges, it's completely dead. Come to the ridges like some. Okay, and this is a dielectric pillar, aluminum oxide on silicon dioxide.
Or questions?
Which ASL you have, you were showing in the strain profile,
Yes.
which you have with the ASL. You have much better resolution with the ASL.
Yes. Yes.
So, I mean, like in the region, because you showed these as rather abrupt.
Yes.
Like,
yes.
for instance,
Yes.
the quantum well formation,
Yes. Yes.
type 2 band jump,
Yes.
type 1
Yes.
range.
That's right.
But you can see the profile also.
We can actually see the profile. So if we really want to mimic that as a graded junction, if that's what you're doing, yes, we can absolutely do that since we have the exact strain values. So on a 3D strain map is there. You take up energy profile commensurate with that. You can do a Poisson equation calculation. Yes.
No, and also directly, so you would, from the strain profile.
From the strain profile, I would actually have a delta EG. Yeah, that's my only input. Electron affinity remaining same. Okay. Calculate self-consistently where the Poisson thing lies, where the EF lies. That's it.
More questions? Okay, if not, then let's thank Professor Joy Mitra once again.
Just one minute. Here, aluminum oxide, you
Yes.
have gone on to that.
Yes.
Here, the dielectric in the environment also plays on the efficiency elements, right? Not only the your strain. I think this is
Yes. So that was really the question. That the luminescence. The fact is luminescence enhancement.
Yes.
Where is it coming from? Is it from strain or is it from plasmonic effect, near field effect for gold? Let's say. Okay. If there was really charge transfer, yeah, charge transfer could happen both ways depending on the energetics. Either from the MOS2 to gold. Okay. The opposite has also been reported depending on the proximity effects, depending on the size of the particles involved. Yeah. So I am interpreting it, correct me if I'm wrong, but I am interpreting as a vindication that the primary effect, therefore, since this is a dielectric, okay, gold had a very large electron sea around it. Right? This is devoid of that. This is a dielectric underneath. Okay. So charge transfer effects, yeah, I cannot negate it. But the effect of the large electron sea and anything ensuing from it is probably not there. And in both cases, I see enhancement.
this is partially not only strain.
Yeah.
It is also because of the radioactiveness of the RNA of the
Sure. Absolutely.
because on the SI it is very much lower. When you put in the elder period, then it's extremely high.
Yes.
It's okay. This is good scientific.
Okay, let's thank Professor Joy Mitra once again. And please answer. I hope so. Ah, it's there.